So we're going to use a different method now. You've used interval bisection and decimal search, their changes of sign method. We're now going to use a fixed point iteration method. We're going to start with Newton-Raphson method. This is going to be used to solve the equation x cubed minus 3x plus 1 equals 0. Now remember, the language is very important. We've got a function, f of x is x cubed minus 3x plus 1, and we're going to use the graph y equals f of x to solve the equation f of x equals 0. We've got the graph here. You can see, because it's a cubic, a positive cubic, it's got the shape that we would expect. There are 2 turning points and there are 3 roots. There are 3 points where the graph cuts the x-axis, so remember that's where we're looking at, because that's the points where the value of f of x is 0. So we have 2 roots there, and the 3rd root is there. They are irrational roots. We can't solve this equation algebraically, and so we are going to use this method. The first thing we're going to do is to do an integer search, exactly like we did with the interval bisection, and you can identify your intervals where the roots lie by using the change of sign in f of x. We have a change of sign here, -1 to 3, so one of our roots is -2, -1 in that interval. We have another change of sign at this point here between 0 and 1, so that's the second interval, and then we have a third change of sign between 1 and 2, and that is reflected in the graph, because you can see that those are the intervals where the graph cuts the x-axis. So having identified where the roots lie, we're now going to find one of those roots using the Newton-Raphson method. And we're going to find the root in the interval 1, 2. The diagram that I've got here now actually shows 2 roots, the one in the interval 0, 1, but we're going to try and find and locate this root here in the interval 1, 2. We're going to take one of our integers, either 1 or 2, as the start value. We would tend to use the one that's closest to the root. The root looks as if it's roughly halfway between, so I'm going to take x0 as 2. Now, in the book, they actually use the start value as x1, but I prefer to use the start value as x0 because it's not an iteration, and it would be good to call x1 our first iteration. So we've actually chosen the value of 2 as x0, and we're going to have a look at how that can be used to find our root. The first thing we're going to do is to draw a tangent. There's a tangent drawn to the curve at the point 2, 3, and you can see the blue line is the tangent. The tangent then cuts the x-axis at the point that is closer to the root than our x0 starting value. So we have an x0 value here, which is our 2, and we have an x1 value, which is where the tangent cuts the x-axis. And what we want to find is the value of x1. So in order to find the value of x1, we're actually going to use the gradient of the tangent. So I'm going to draw in a triangle, and you know that the gradient of the tangent is the change in y over the change in x. The height of this triangle is our f of x0, so that's that height, and we know that's actually 3 because that's the value of y, or f of x0 at that point, and the distance along the bottom is going to be x0 take away x1. So the gradient of the tangent is f of x0 over x0 take away x1. Now this tangent is the tangent to the curve at the point 2, 3. The point 2, 3 is also the point x0, f of x0. I've labelled it here. And the tangent at that point is the gradient of the tangent at that point is the gradient of the curve. And we know that the gradient of the curve at that point is the differential. So we know that the gradient is also, so the gradient at the point x0, f of x0 is also f dashed of x0. Is the differential. So I'm going to rewrite our formula, f of x0 over x0 minus x1, and that also equals f dashed of x0. We'll rearrange this, so f of x0 over f dashed of x0 equals x0 minus x1, and we can simply rearrange this so that x1 is x0, take away f of x0 over f dashed of x0. So we've used the tangent to the curve at the point x0, f of x0, and we've generated a formula for how we can find the value of x1. So let's use this formula that we've just generated to find out the value of x1. We know that x0 is 2. We know that f of x is x cubed minus 3x plus 1. And we also need to know our differential f dashed of x, and that is clearly 3x squared minus 3. So we're going to substitute in the value x0 is 2. So f of 2 becomes 2 cubed minus 3 2's plus 1. And f dashed of 2 is 3 times 2 squared minus 3. So f of 2 is clearly 3, and f dashed of 2 is 9. And we can substitute this in our formula. So x1 is x0, which is 2, take away f of 2, which is 3, over f dashed of 2, which is 9. So we've just substituted in all of our values using x0 equals 2, and we've found a value for x1. 3 over 9 is clearly a third, and so x1 equals 1 2/3. And you can see from the diagram that that's a good value. You can see that it sits at a position where 1 2/3 is a sensible answer. So once we have found x1, we want to try and find x2, and what we need to do is to repeat the same process. So here's the next graph. We've now got x1. We know that the value here of x1 is 1 2/3. I'm using a fraction rather than a decimal so that I'm accurate. And again, this diagram has drawn a tangent to the curve. This time, the point on the curve is the point x1, f of x1. And the tangent to the curve is then going to cut the x-axis at this point down here, and that is going to be our x2. And you can see that each progressive x0, x1, x2 is getting closer and closer and closer to the root, and it's actually going to converge on that root pretty quickly. So to generate the value of x2, then we are going to use the iterative formula. At the top, I've given the general iterative formula. This is what we generated on the previous page, except we generated x1 from x0, and we're going to use the same successive formula. So xn plus 1 is generated from xn. And we have got a function x cubed minus 3x plus 1. And so I can put that function into the general formula and create the iterative formula for our equation. And that is xn plus 1 equals xn minus xn cubed minus 3xn plus 1 over 3xn squared minus 3. Now, in order to generate x2, we're going to substitute in x1. So we would have x2 equals x1 minus x1 cubed minus 3x1 plus 1, and that's over 3x1 squared minus 3. So if you, on your calculator, substitute 1 2/3 and use the fraction, make it 5 over 3 is probably easier, and if you use the fraction, you can generate the value of x2. And this time I'm going to give it as a decimal, and x2 is 1.54861111, etc. So what we would then do is we would then use exactly the same iterative process, and we would generate x3 and x4, and we would be looking to generate successive values of x that were the same to 5 or 6 significant figures, depending on how accurate we want our answer to be and our root to be. So this spreadsheet has done exactly the same Newton-Raphson formula, iterative process, and it has generated successive values of x. So this is our x0, this is our x1, x2, x3, x4, x5, x6, and x7. And you can see that we very quickly get to our values being pretty much the same. And actually f of x here, although it isn't exactly 0, but the Excel spreadsheet can only give it to a certain number of decimal places, which shows that we get very, very close to a solution of our graph, because a solution of our equation, because we want f of x to be 0, and although it isn't exact, it will be as exact as it can be on an Excel spreadsheet. So we can say that the root of the equation is 1.5321 to 5 significant figures. As we've done before, we're going to give error bounds, and we're going to use those error bounds to confirm that we have a change of sign. There is indeed a change of sign, and so we can say that x equals 1.5321 is correct to 5 significant figures. And it's not taken many iterations. If you look on the left-hand column of our spreadsheet, you can see that the values of x3 and x4 are different 5 significant figures, but x4 and x5 are the same. So it has taken 5 iterations. We can't say 4, even though it's found the root to 4 iterations, then it needs the 5th iteration to confirm that 5th significant figure. So here are 2 other spreadsheets to find the other roots. In the first spreadsheet, x0 is taken as -2, and in the second, x0 is 0, and you can use these spreadsheets to find the other 2 roots to 5 significant figures and verify those roots using error bounds.